table in Chapter 9 of the National Electrical Code, NEC, specifically Table 9, provides data on conductor properties. It lists the ampacity of conductors based on wire size and insulation type. Each American wire gauge, OG, entry typically has two ampacity values. The top number represents the ampacity of a single conductor when it is in free air. The bottom number indicates the ampacity of a single conductor when installed in a raceway or cable. Ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating and damaging the insulation or surrounding materials. Several factors determine ampacity, including the conductor's size, the insulation type, and the ambient temperature. A conductor in free air usually has a higher ampacity than the same conductor in a raceway or cable. This is because free air allows for better heat dissipation. The air surrounding the conductor helps to remove heat generated by the current flow. In contrast, a raceway or cable can trap heat. The insulation and other conductors within the raceway impede heat dissipation. When selecting a conductor, it is important to choose the correct ampacity for the installation method. If the conductor is to be installed in a raceway or cable, use the ampacity value specified for that condition. Using the free air ampacity in this situation could lead to overheating and potentially dangerous conditions. For example, a 12 AW GTHHN wire might have a free air ampacity of 25 amps. The same 12 AW GTHHN wire in a raceway or cable might have an ampacity of only 20 amps. If you were installing this 12 AW GTHHN wire in a raceway, you would need to use the 20 amps ampacity rating. Failing to do so could overload the conductor and create a fire hazard. The NEC provides tables to correct ampacity for ambient temperature and the number of current-carrying conductors in a raceway. These correction factors ensure that the conductor operates within its safe temperature range. Firstly, ambient temperature correction is important when the surrounding temperature is higher than the temperature rating of the conductor. Secondly, the number of conductors in a raceway affects the heat dissipation of each conductor. More conductors mean less efficient heat dissipation, which necessitates reducing the ampacity. The NEC provides detailed guidelines on how to apply these correction factors to ensure safe and compliant installations. Always consult the latest edition of the NEC for the most up-to-date information and requirements. Understanding these concepts is crucial for electrical safety. Always consult with a qualified electrician for any electrical work. It is important to consider the practical implications of conductor ampacity in various installation scenarios. Firstly, consider a scenario where multiple conductors are bundled together in a conduit. This is a common practice in many electrical installations, but it can significantly affect the ampacity of the conductors. The heat generated by each conductor can build up within the conduit, reducing the overall heat dissipation. To address this, the NEC requires the application of diluting factors when the number of current-carrying conductors in a conduit exceeds a certain threshold. These diluting factors reduce the allowable ampacity of each conductor, ensuring that the temperature rating of the insulation is not exceeded. Secondly, consider the impact of ambient temperature on conductor ampacity. In environments with high ambient temperatures, such as industrial facilities or outdoor installations in hot climates, the ampacity of conductors must be adjusted to account for the increased heat. The NEC provides tables that specify the appropriate ampacity correction factors for different ambient temperatures. These correction factors reduce the allowable ampacity of the conductors, preventing them from overheating and potentially causing a fire. Thirdly, consider the type of insulation used and the conductors. Different insulation materials have different temperature ratings, which directly affect the ampacity of the conductors. For example, THHN insulation has a higher temperature rating than TW insulation, allowing THHN conductors to carry more current than TW conductors of the same size. The NEC provides tables that list the ampacity of conductors based on their insulation type. Fourthly, consider the length of the conductors. In long runs of conductors, voltage drop can become a significant issue. Voltage drop occurs when the voltage at the load end of the conductor is lower than the voltage at the source end. This can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, it is important to select conductors that are large enough to carry the required current over the given distance without excessive voltage drop. The NEC provides guidelines on how to calculate voltage drop and select conductors that meet the voltage drop requirements. Fifthly, consider the type of load being served by the conductors. Different types of loads have different current characteristics. For example, motor loads have high inrush currents when they start, which can cause conductors to overheat if they are not properly sized. The NEC provides specific requirements for sizing conductors for motor loads to account for the inrush current. Understanding these practical considerations is essential for ensuring the safe and reliable operation of electrical systems. Always consult the latest edition of the NEC and work with a qualified electrician to ensure that your electrical installations meet all applicable requirements. In addition to the factors mentioned above, it is also important to consider the following when selecting conductors. Firstly, the available space for the conductors. In some installations, space may be limited, which can restrict the size of the conductors that can be used. Secondly, the cost of the conductors. Larger conductors are generally more expensive than smaller conductors. Thirdly, the ease of installation. Larger conductors can be more difficult to install than smaller conductors. When selecting conductors, it is important to balance these factors to choose the conductors that are best suited for the specific application. The NEC provides a wealth of information on conductor ampacity and selection. By carefully considering all of the relevant factors, you can ensure that your electrical installations are safe, reliable, and code compliant. Remember, electrical work can be dangerous. Always consult with a qualified electrician if you are not comfortable working with electricity. Always turn off the power before working on any electrical equipment. Use appropriate safety gear such as gloves and eye protection. Follow all applicable codes and regulations. By following these safety precautions, you can help to prevent electrical accidents. The ampacity of a conductor is a critical parameter that must be carefully considered when designing and installing electrical systems. Selecting conductors with the appropriate ampacity is essential for ensuring the safe and reliable operation of the system. Firstly, insufficient ampacity can lead to overheating, insulation damage, and potentially fire hazards. Secondly, excessive ampacity can result in unnecessary costs and increased installation complexity. Thirdly, the NEC provides detailed guidelines and tables for determining the appropriate ampacity of conductors based on various factors, including wire size, insulation type, installation method, ambient temperature, and the number of current-carrying conductors in a raceway. Fourthly, understanding these guidelines and applying them correctly is crucial for ensuring code compliance and preventing electrical hazards. Fifthly, in addition to the NEC requirements, it is also important to consider the specific requirements of the equipment being served by the conductors. Some equipment may have specific ampacity requirements that exceed the minimum requirements of the NEC. Sixthly, it is always best to err on the side of caution and select conductors with a slightly higher ampacity than required. This can provide a margin of safety and help to prevent overheating in the event of unexpected load increases. Seventhly, regular inspection and maintenance of electrical systems are essential for identifying and addressing potential ampacity-related issues. Over time, conductors can degrade due to heat, moisture, and other environmental factors. This degradation can reduce the ampacity of the conductors and increase the risk of overheating. Eighthly, during inspections, it is important to check for signs of overheating, such as discolored insulation, melted connectors, and a burning smell. If any of these signs are present, the conductors should be replaced immediately. Ninthly, proper termination of conductors is also critical for ensuring their ampacity. Loose or corroded connections can create resistance, which can generate heat and reduce the ampacity of the conductors. Tenthly, all connections should be clean, tight, and properly insulated. 11th, understanding the principles of conductor ampacity is essential for anyone involved in the design, installation, or maintenance of electrical systems. By following the NEC guidelines and taking appropriate safety precautions, you can help to ensure that electrical systems are safe, reliable, and code compliant.